Welcome to The Explainer. We're diving straight into a brand new, paradigm-shifting cosmic detective story today, straight from the deep universe, all thanks to the James Webb Space Telescope. So, settle in and keep your eyes on the details as we unravel this cosmic cold case. Ever since James Webb started beaming data back to Earth, it's essentially rewritten our entire understanding of the early universe. But out of all the galaxies, the stars, the giant cosmic structures it's imaged, there is one specific population of objects that has the astronomical community absolutely fascinated. And honestly, a little stumped. These things are incredibly distant, totally mysterious, and they are challenging literally everything we thought we knew about how black holes and stars form in the deep cosmos.
Okay, let's dive into this. Our primary suspects are known as little red dots, or LRDs. So what are they? Basically, they're highly compact sources found at extremely high redshifts, meaning they existed deep in the cosmic past, more than 11 billion years ago. They are surprisingly abundant all over the early universe, but their absolute defining feature, the smoking gun that gives them away, is this distinct V-shaped spectral profile. Before we dig into the forensic evidence, we really need to understand just how disruptive these little red dots have been to our standard cosmic models.
All right, part 1. A cosmic paradigm shift.
So, let's look at the competing theories. For a while, scientists thought they had a pretty solid open and shut case. The prevailing theory was that little red dots were powered by accreting supermassive black holes. The thinking was that these black holes formed early on and were just wildly feeding on surrounding gas. Makes sense, right? Well, there was a massive problem. They completely lack the X-ray emissions or the mid-infrared dust signatures you would absolutely expect to see from a typical black hole. Because of that, researchers have proposed a radical new hypothesis. What if we aren't looking at black holes at all? What if, instead, we're looking at globular clusters in formation, surrounding a single, incredibly short-lived supermassive star? We are talking about a star with the mass of maybe 50,000 suns, just bursting to life in the intensely dense core of a young star cluster. It's a total game changer.
Let's decode that V-shaped spectrum to see the evidence.
And this brilliantly illustrates exactly what we're talking about. That V-shape literally maps to a dual origin. On the left side of the V, you've got the blue rest frame ultraviolet light. And that perfectly matches the highly energetic output of a very young stellar population, the newly forming star cluster. Then you get a sharp inflection, turning into the red rest frame optical light on the right side. That side is beautifully fit by a modified blackbody spectrum, representing that absolute monster of a supermassive star sitting right in the cluster center. The V-shape is basically just the transition between the light dominated by the cluster and the light dominated by the supermassive star. But like any good detective story, we've got a twist, a discrepancy. If you look really closely at the data, the observed optical light doesn't actually match our standard, pre-existing models for supermassive stars perfectly. It turns out the observed little red dots are actually cooler in temperature, yet somehow far more luminous than theoretical hydrostatic models predict. So why on earth would a star be cooler but brighter?
Well, the answer comes down to some seriously extreme physics. Notice how the dark blue dots, representing our little red dots, sit way above the dashed light blue line, which we call the Hayashi line. Now, the Hayashi line represents the maximum luminosity of a star resting in normal hydrostatic equilibrium. But our supermassive star is so overwhelmingly bright, it's emitting right near its absolute Eddington limit that it literally cannot hold on to its outer layers. Think of it like this. The star is burning so furiously that the radiation pressure actually blows off an incredibly thick outer envelope of wind. This material expands outward, creating an extended photosphere that acts like a giant glowing cloud around the star. Because this cloud is physically enormous, it makes the star look much larger and therefore cooler than its core actually is, all while maintaining this incredibly high overall luminosity. It's wild.
Now let's fast forward and see how this evolves to the present day. What's really interesting here is how we can use cosmic time travel as an investigative tool. If you take the initial mass function of these ancient little red dots from over 13 billion years ago, that's redshift 7, and you ask, okay, if these really are globular clusters in formation, what happens if we let them passively evolve over 13 billion years? The predicted evolution matches up beautifully with the actual observed mass distributions of globular clusters in our modern Milky Way and the Virgo cluster. The mass function of these ancient dots perfectly shapes into the mass function of the local globular clusters we see today. And to make that 13 billion year math work, we have to talk about mass loss. Specifically, a constant mass loss rate of roughly 10 solar masses every million years. Over billions of years, star clusters lose mass through stellar evolution, supernova, and just getting tidally stripped by their host galaxies. This steady, relentless process literally strips away and completely destroys the smaller, lower mass clusters over time, leaving only the most massive, dense survivors. That is exactly why the modern distribution has that characteristic curve we see.
And you know what? The math gets even better. If you take the total number of little red dots forming across all those ancient cosmic epochs, and you calculate exactly how many should survive to the present day, you get a number density of roughly 0.3 per cubic megaparsec. So why does that matter? Well, because the actual observed number density of globular clusters floating around our own galactic neighborhood today is right between 0.5 and 1.5 per cubic megaparsec. So order of magnitude speaking, the sheer number of these ancient objects perfectly matches the abundance of the globular clusters we see locally today.
But there's a catch. We need to talk about the missing metal-rich clusters. So if you look at the timelines, they align flawlessly for ancient, metal-poor Milky Way globular clusters. They both peak deep in the cosmic past. But there's a missing demographic in the data. What about the younger, metal-rich globular clusters? The timeline lines up beautifully for the metal-poor ones, but there is just this glaring absence of little red dots that would match the younger, metal-rich clusters. So where are they?
Astronomers are currently proposing two possible solutions to this missing evidence problem. First, metal-rich clusters typically form much closer to the centers of massive galaxies. So the missing little red dots might actually be there, but they're completely hidden by the overwhelmingly bright light and dust of their neighboring galactic bulges. We literally just can't see them. The second solution is a bit more physical. It suggests that supermassive stars simply can't form in high metallicity environments. You see, making a supermassive star requires insanely high stellar densities to trigger these runaway stellar collisions. If high metallicity environments just don't allow clusters to reach those extreme densities, well, the supermassive star never forms. And without the star, you never get that V-shaped spectrum that defines a little red dot in the first place.
So how are astronomers actually testing this theory? It comes down to catching them in the act. If little red dots truly are globular clusters in formation, they're going to carry some very specific chemical fingerprints. Astronomers predict we'll find enhanced levels of helium and nitrogen. On top of that, they expect to see distinct anti-correlations, meaning populations that are high in sodium but low in oxygen, and high in aluminum but low in magnesium. These rapid-fire chemical predictions are exactly what local globular clusters show today, and it's all due to the extreme nuclear burning inside a supermassive star. If James Webb can peer closely enough to spot these specific fingerprints, the supermassive star theory might just win this whole thing over the black hole theory.
As we wrap up this explainer, I want us to just slow down for a second and bring these massive cosmic implications right back to our own backyard. If this theory is correct, it means the mechanics of the deep, distant early universe have left physical artifacts orbiting our very own galaxy right now. It means we aren't just looking at isolated, ancient anomalies, we are looking at the fiery birth pangs of structures we can point our backyard telescopes at today.
Which leaves us with this incredible, thought-provoking cliffhanger. If a little red dot really is a forming globular cluster powered by a 50,000 solar mass star, well, that star had to die eventually. And when a star like that dies, it collapses into a black hole. Does this mean our local globular clusters, the ones orbiting the Milky Way right now, are secretly hiding intermediate mass black holes in their dense centers? Are the invisible ghosts of these ancient, supermassive giant stars lurking just outside our galaxy, waiting to be found? It's a thrilling question and a perfect reminder of why we keep looking up. Thanks for joining me on The Explainer.